All right, so I'm Brian Paul, and I'd also like to thank all of you for attending today. I think I have about a 15-minute time slot here to do a bit of a high-level overview of the components in gallium and MESA too, because it's a big part of this as well. Basically, I wanted to cover, for example, what graphics APIs do we support? That is, what will the outside world see of this stack? Going a bit deeper, that also relates to which Windows system interfaces do we support. And then finally, which devices, which graphics processors or GPUs or software implementations do we support? And then finally, I want to give a MESA status report as well. So taking just a bit of the stack out of Keith's earlier diagrams, here's the bit I'm going to talk about now. So right below our application, of course, we have various graphics APIs, such as OpenGL, OpenGL ES, OpenVG. Underneath that, well, you can think of like as Keith said, the Gallium interface is really just an API. There's really no implementation to it. And the implementation underneath can vary a great deal. It's the same story with the public APIs that we're aware of, like OpenGL, OpenGL ES. If you look at the specification, it tells you here's the interface, but it doesn't really tell you what the implementation details are. So in Gallium, the state tracker that Keith described is basically just another name for the graphics interface that we're going to support. And that's the part of the stack which converts the user visible API, like OpenGL, into the Gallium interface. So in this layer, this is where we do things like convert your draw calls to the Gallium format, or convert blending modes to the Gallium format. We also do things like simplify high-level OpenGL operations, like we convert GL draw pixels into a textured polygon draw. We do special things for GL clear, etc. So this is the kind of things that the state tracker does. So right now we have state trackers for OpenGL 2.1, which is actually MESA. We have state trackers for OpenGL ES versions 1.0, 1.1, and 2.0. And we also have OpenVG. Those are the public graphics APIs that we support. As Keith said before, we also have this x.org state tracker, which isn't directly visible to end users, but it's another state tracker which converts basically the X server's rendering needs into what's provided by the Gallium interface. And so then also off to the side of these rendering interfaces are the Windows system binding interfaces that we know, like GLX and EGL. So the OpenGL 2.1 state tracker is basically MESA plus a new component which interfaces MESA to the Gallium interface. And that's really just another MESA device driver. But instead of targeting a certain GPU, it targets the Gallium interface. So what do these pieces do? Well, we have core MESA. And some pieces of MESA that we've developed over the years weren't necessary for Gallium, and we've omitted them. But there's still an awful lot that we do use for Gallium. And so, for example, all the underlying code that handles OpenGL API functions is still there. All the stuff that has to do with context and state management. The other big component is the GLSL compiler. Another piece we used is the VBO, or Vertex Buffer Object module. And that's basically a module which takes all the various ways that OpenGL can draw something and boils it down to basically one unified drawing call. So whether you use GL begin and end, GL draw arrays, GL draw elements, GL eval mesh, or call it display list, that all eventually goes through the VBO module and gets boiled down into nice, tidy vertex buffer objects and vertex arrays. So we reuse that part as well. Let's see. Yeah, so the other new piece then we developed for Gallium is this new MESA device driver. We also often call that the MESA state tracker. We really have several different names for the same component. But anyway, this is the piece that basically hooks into MESA's device driver interface and takes those calls and converts them into Gallium calls. Some are really simple. So at some point in MESA, when you call GL clear, it calls CTX arrow driver.clear, which is a driver hook. That goes into the state tracker, and that's where we either call Gallium directly to clear a buffer or maybe draw a solid colored quad instead. We also have things like functions for creating textures, buffer objects, synchronization objects, setting GL state for blending, rasterization, texture sampling. And if you were to look at the MESA tree, which we will later, this block of code, this MESA to Gallium adapter, lives in source/MESA/state tracker. And that's really just there for historical reasons. There's actually one or two other places that this is probably better suited, so we might move that someday. So as a point of comparison, if you're curious about how we used to do things and how we do things now, on the left you see sort of the conventional MESA driver stack, and on the right we see sort of the MESA plus Gallium driver stack. So on the left side we had core MESA and the shading language compiler, and sort of off to the side we also had these modules for transform and lighting and software rasterization and a few other bits. And then we had the MESA device drivers themselves. And as Keith mentioned before, these device drivers were kind of large, kind of clunky. There's quite a bit of redundant code between the different drivers. And we had actually quite a few of them, though. We had drivers for a whole bunch of ATI GPUs, most of the Intel GPUs, and others. There's a group working who developed drivers for NVIDIA chips, SIS, VIA. So on the right, we have the new MESA Gallium stack. And again, we have core MESA and the shading language compiler. And then underneath that, we have the MESA state tracker, the MESA Gallium driver. And this sort of, well, it does two things. It adapts MESA to the Gallium interface, and it also lifts a bunch of code that used to be in these individual DRI or hardware drivers into a common reusable package. So for example, GL draw pixels. It seemed that each driver was either A, falling back to slow software memcopy type implementations, or rolling their own version of drawing a textured polygon. So now with the new MESA Gallium stack, that kind of code has all been moved up into this reusable state tracker, this adapter module. And so now device driver writers don't need to worry about GL draw pixels or special cases of GL clearing or GL copy pixels or GL blit frame buffer. Those things have been done once, and they'll be reused for all possible drivers in the future. So that makes the stack more organized, and most importantly, makes the drivers smaller and the Gallium interface smaller and simpler. So we also have support for OpenGL ES and the EGL interface. We developed the OpenGL ES state trackers supporting versions 1.0, 1.1, and 2.0 back in 2008 at Tungsten Graphics for a contract we're working on. And that code is all in open source. It's in the MESA tree, but it's currently on a branch, actually two branches. I put that code into the MESA tree on a branch back in May. Just got at the point where it all built and ran and did what it was supposed to do. And I had planned to merge that to MESA master a long time ago, but just being so busy with other things, it hasn't happened yet. In the meantime, somebody came along through the open source community. His name is Chai Wu, and he jumped all over this stuff, and he's been just doing some really fantastic work. He's been sort of cherry picking out of this OpenGL ES branch, freshening everything up, cleaning it up, and I set up a new branch for him. And so I think within a couple of months or so, we're going to merge that to master, and we'll have nice, fresh, up-to-date OpenGL ES state trackers and interfaces. I'm actually going to go into this in a bit more detail later, but I want to tell you that OpenGL ES is implemented as a subset of MESA. For a bit, we were thinking of writing brand new state trackers from scratch without any legacy stuff at all to do OpenGL ES. But as it turns out, and not surprisingly, there's a lot of stuff that can be reused between OpenGL ES and a full OpenGL. All the stuff, for example, has to do with state setting and texture objects and buffer objects. It's all the same, so it's silly to fork the tree effectively and have these things at two different places. So OpenGL ES is really just a subset of MESA. Let's see. Yeah, so I'll go into more detail about those things, I think this afternoon after lunch. I also want to mention at this point, talking at the high level, we have an OpenVG state tracker. And again, this is a module which converts OpenVG API calls into Gallium. And that adapter, or that interface, or the block of code that connects these interfaces is our state tracker. Zach has been working hard on that, and he'll go into more details about that this afternoon. So the other part of this, of course, in addition to the rendering APIs, are the Windows System binding interfaces like GLX and EGL. Well, we've had GLX for a long time now, at least 10 years in open source, I think. And so that basically continues to work the way it always has, where, at least in the MESA DRI world, where libgl is basically just a thin layer which goes off and dynamically loads a DRI driver module based on whatever GPU you have in your system. And with Gallium, the bits that are in these DRI drivers has changed, but it looks all the same to the libgl. So we didn't break anything in that interface there. We've also, well, since I first did MESA way back in '93, I guess, we still have a software emulation of GLX, which presents the GLX API to applications when, in fact, the X server does not support the GLX extension or anything like that. Basically, everything is converted into xlib calls. And that still, to this day, has been still useful for testing and debugging purposes. So we still have that, and it's fully supported with Gallium. The other Windows System binding interface we care about is EGL. And that was the Windows System interface developed for OpenGL ES. But it also works for any number of other rendering APIs. You can use it with full OpenGL. You can use it with OpenVG and some other things. The nice thing about EGL is it doesn't have any built-in hard dependencies on X like GLX does. So EGL can work with X or other Windows systems like Windows. And we also have a few extensions to EGL which allows you to use it without a Windows system at all. So you can talk directly to a full screen, take over the screen basically without an X server or anything like that. And we also have a component for EGL, and again, I'll go into more detail about this later. It's basically, we have a shim layer, which is a very thin driver that EGL can load, which then in turn can load a conventional GLX driver. So all these drivers we have for GLX, I mentioned earlier, can be reused with EGL. We have a sort of a translation layer in there. So this is the other big interesting bit. What device drivers do we have for Gallium right now? Which GPUs do we support? What kind of software rendering options do we have? So first of all, we have SoftPipe. And this was one of the first drivers we developed, of course, for Gallium. We consider it the reference driver when we have questions about how should the Gallium interface be interpreted or used. We want to probably look at the software driver to see what's going on there. It's not a terribly fast renderer, but we try to make it as correct as possible. So to address the speed problem, we developed another new driver called LLVM pipe. And this is based on LLVM, which is the open source project, which is basically a new compiler construction set framework. And so we're using LLVM to do runtime code generation. And I'm sure you all understand that, but basically, with SoftPipe and the conventional MESA software rasterizer, the big problem you have to deal with is combinatorial explosion of states. There's like a million different state combinations that can apply to drawing a triangle, and you just can't optimize for all of them with if, then, else's and switch statements. Ideally, we want to generate custom triangle rasterizers and things at runtime based on the current state. And now with shaders, we want to convert our GLSL shaders into machine code, and that's sort of what LLVM pipe does. And Jose will go into greater detail about that this afternoon. The first hardware driver we did for Gallium was for the Intel 915, 945 class hardware. And that driver is pretty much complete. works pretty well. One interesting comment I'll make is that Gallium was designed for programmable hardware. We didn't really have any interest in supporting old fixed function hardware. So we assume that the hardware has a programmable vertex shader and fragment shader. In the case of the 915 chip, though, it only has programmable fragment shading, not vertex shading. So inside of Gallium, we have a number of reusable modules, optional pieces that you as a driver writer can elect to use or not use or write your own. And one of them is basically a software vertex processor. We just call it the draw module. But it handles things like converting OpenGL's assorted vertex formats into nice uniform float formats, doing vertex shading, all the vertex per vertex transformations, clipping, and things like wide lines and point sprites and things like that. So the 915 driver uses that optional stuff to fill in the bits that the chip can't do itself. More recently, we've started a driver for the Intel 965 GPU, and that does have full vertex fragment shading. So you'll see in that driver that we will not use the draw module, ideally, and will take full advantage of the hardware. Next on the list is the cell driver. Back at Tungsten Graphics, we had some funding to develop a cell driver. And but when we were acquired by VMware, we had to set that aside. But the code is open source, and I was working on it in my spare time a bit, but haven't had much time for it lately. But the driver is functional. It renders a lot of things correctly. Quite a few MESA demos run just fine. There's some holes in it, and it's not being actively developed right now. There were a few people in open source who had sort of latched onto it and were doing some work, but it's really tailed off a lot in the past 6 months. So there's other Gallium drivers for some GPUs out there that we personally haven't worked on, but the open source community has jumped on. And those include drivers for the various NVIDIA chips, also known as the Nouveau driver. These are some of the guys who have been involved in that: Ben Skeggs, Stephen Marchson, Christoph Buehler. There's also a driver underway for the AMD ATI R300 GPU. Corbin Simpson, Cooper Yan, and Nikolai Hanel have been working on that. I personally haven't used these drivers, so I'm not quite sure what kind of state they're in, but I think they're running some things. And so, I mean, just the point I think here is to say that we have this open source architecture and infrastructure, and people have just jumped into it, and with surprisingly little assistance from us, have gone off and developed these new drivers, which I think is a really positive reflection on the architecture. Okay, so a bit more about plans for Core MESA. And again, I think we have a time slot towards the end of the afternoon where I'll go into more detail about Core MESA and OpenGL support. But here's some of the highlights. So going forward, we of course want to support OpenGL 3, and that's got some major new features like geometry shaders, new kinds of texture formats, new ways of rendering. The Gallium interface doesn't support all these things yet, but we'll be doing that fairly soon, I think. MESA's GLSL compiler it's been functional, pretty much fully functional for about 2 years now. But we really need to do some work on it to sort of bring it to the next step and prepare it for the future. Right now, it's pretty much entirely a homegrown compiler. Everything from tokenization through parsing, through code generation, optimization. It's all homegrown. And because of that, it's not as good as it should be. The compiler's a bit slow. It doesn't produce the best code. And it's a bit hard to maintain. So we want to address all those things in the future. And so specifically, Michael's developed a new preprocessor. Ian Romanek has been working on a new YAC-based parser. And we also want to use LLVM. LLVM the biggest thing it brings to the table for us is this optimization framework. When you look at a GLSL compiler or a shader, it looks an awful like C code, and a lot of the optimizations you want to do to an ordinary C program, you want to do in your shaders as well. And rather than try to spend many man-years writing optimization passes for the GLSL, we think it'd be best to use something else that other people are developing for us, basically, and that's LLVM. Going forward, and this has always been an ongoing thing for me in MESA, is to do code refactoring and housekeeping and cleaning things up in core MESA. When we did the OpenGL ES work last year, it was another reason to go in and start repartitioning source files and things. So for example, at one point we had all of the texture setting state functions in one file. So text parameter, text CNV, text gen, text image were all kind of mixed together. In OpenGL ES, we don't have some of these things like text gen. So I went in and broke up these files into smaller pieces, partitioning code a little bit better so that when you build an OpenGL ES stack or driver, you can really omit big chunks of code that you don't need. And there are people out there who are very interested in automated code coverage tools. And anything you can do to reduce the number of lines of code that have to be tested and covered, they're happy to see this stuff be factored away. Also in the spirit of cleaning up and repartitioning things, I have some thoughts on rearranging the structure, the MESA source tree, specifically in the areas of the GLSL compiler and the GPU program code. There's a lot of possible cleanups we can do there. I want to do things, refine some data structures in MESA. We had textures for a long, long time, then came render buffers, and we just sort of did that as a separate set of data structures in MESA. And of course, nowadays with render to texture and things like texture buffer objects, all these different kinds of buffer type things have sort of merged together. And while we've done a good job of merging these things, these concepts in Gallium, we haven't done as much of that in core MESA. And I think by revisiting these data structures, unifying and cleaning things up, we can make things better everywhere. Miscellaneous things, there's the MESA device driver interface has quite a bit of stuff in it that really doesn't need to be there. So little by little, I've been sort of pulling things out of there, making it smaller and simpler. We have quite a few legacy drivers in the MESA tree, things like for the old Matrox chips, some early ATI chips, 3DFX drivers. I'm tempted to toss those aside someday, and that'll let us get rid of some more legacy code in MESA that I don't think people would miss. So, and I think that, yeah, so that's pretty much the status of the all the open source pieces at Gallium. And we'll go into more detail about those things this afternoon. Did anybody have any questions about any of that material?